Okay. I guess I'll get started then. It's a little early, but that's fine. So, this is lecture 5 on the YouTube series and recording for Artin? Artin Abstract Algebra, whichever way you pronounce it. We're going to be covering the vector spaces section of it, which is the subspaces. I was told we did not cover subspaces yet, so that's fine. We'll cover that, and then we'll probably also cover. Will be covering basis, dimension, and some other stuff there. We're basically gonna power through like half of the chapter. The later half contains some other stuff, but I'll leave that for next lecture. Okay, so here's the definition of a subspace that they use in the book. There's 3 main properties. The first is vector addition. I should also note that this is an R of n. They specified that in 3.1. They kind of jumped around a little bit. They did subspaces first, and then fields, and then vector spaces in general, which I'm not used to, but that's okay. So there's 3 properties here. There's vector addition, scalar multiplication, and then it has to contain the 0 vector. So there's 3 properties here that need to be satisfied. The book also mentions that there's a faster way to write these conditions. It just has to be non-empty, and any number of vectors and scalars can be multiplied and added together, and that will also be in W. I think the harder part to see here is that this is equivalent. Oh yeah. Oh, I thought someone was asking something. That's okay. I guess the harder part to see here is that the 0 vector is equivalent here, but that's fine as long as it contains something. You can get the 0 vector. So yeah, we're going to look at some examples. One example is the null space that they use in the book. I think it's more of a complicated example, but if you are familiar with linear algebra, it shouldn't be too bad. He writes the null space in terms of matrices here. So the null space of A for a matrix M by N with entries in R is all of the vectors that take it to 0. Yeah, he writes vectors as like capital here. I personally wouldn't write it like that, but I just followed sort of the notation and concepts of the book pretty closely. Let's see here. So yeah, the null space is in fact a subspace because 0 is a null of A, because A times 0 is 0. Any 2 vectors in the null space of A, we can add them together and distribute them. So this is using like matrix properties that you probably are already familiar with. So I don't have to explain it too much. So yeah, that's one example. Another example is the 0 subspace and the full space, which is just the 0 vector. It's the smallest subspace. And there's also the entire space itself. So those are 2 like they're called trivial subspaces of a given like vector space. And then there's also proper subspaces, which are ones that are not trivial. So more than just a 0 vector and less than that of the entire space. Somewhere in the middle. By the way, let me know if you have any questions, like you send them in chat, and I'll read them, and I'll pause and like answer anything. Null space in the kernel? So I think the kernel, that's actually a good question. Yeah. So I think null spaces has to do with matrices. And kernel is to do with groups. But I think they're very similar. They're very similar concepts. Yeah. Yeah, I think I typically see null space with matrices. That's usually how they're introduced. But yeah, I think they're exactly the same. Yeah, no, that's okay. That's okay. Yeah, they're essentially the same thing. Okay. So proposition 3.1.4, which is in the textbook, if W is a proper subspace of R squared, and W, little w, is some non-zero vector in W, in big W, then the subspace W consists of all scalar multiples, CW of W. That's a lot of W's. And distinct proper subspaces have only the zero vector in common. Basically, this is talking about lines in R squared, because the only proper subspace of R squared would be a line. And this is basically saying two things. They consist of scalar multiples and that they only share the zero vector. And so one way you can visualize this is in terms of like lines, like this huge line here. There's a vector that can be scaled in like any direction. And then same with this one. So yeah, it's like a little Tix diagram. So the proof, since W is a proper subspace and contains some non-zero vector W, then it must be a line through the origin. And any line through the origin will be exactly scalar multiples of that W. So any vector can be written as a scalar multiple of that little w, which is what we want to show here. And then to continue the proof, to just show that they're distinct, proper subspaces only have the zero vector in common. Well, if we had two proper subspaces in R squared, and there was some non-zero vector, like say V, in both spaces, we could write them in terms of scalar multiples of W1 and W2. But then this would mean that we could rewrite one vector as a scalar multiple of the other, which is not good because this would mean that W1 and W2 are essentially the same set. They're the same line because we can just scale one to get to the other. So this would contradict that they're distinct subspaces. Every null space. Yeah. Oh, this is like a little question I didn't see mentioned in the chapter, but it might be in the exercises, but this is one that I came across when I was doing I was taking a linear algebra class. So if W1 and W2 are subspaces of R squared, then W1 union W2 is a subspace of R squared. This is just something to think about. You can try solving it. I gave a little hint at the bottom, but yeah. I just thought this would be a cool little question to throw in here because we're talking about subspaces. Now, true? You think this is true? Okay. I believe it's false, but yeah, I think it's false. Yeah. Yes, yeah. You can separate R squared into X and Y. which if you union those together. Wait, now I'm thinking, did I write this correctly? If W1. Yeah, I'm trying to think. I might have wrote this wrong, actually. I'll double check on this. I'll double check. I might have wrote this wrong. Yeah, I believe this is false. It's something like this, though. Yeah, I'll double check that. So the next part, we'll talk about ordered. And yeah, the intersection of subspaces is definitely a subspace. Yeah. The ordered and unordered sets. So in the textbook, he writes an ordered set with, what is this, like just curly brackets? Not curly brackets, closed brackets, I guess. Round brackets. And the curly braces are for an unordered set. Yeah, this is like, I guess, kind of standard notation. Although this might be a little confusing if you're talking about points, but I don't think it matters in this context. So the next definition we come across is linear combinations. This is like ripped straight out of linear algebra, so nothing new. If we have vectors, there exists scalars such that v can be written as can be written as a vector. So yeah, nothing too exciting. And then spanning set as well, ripped straight out of linear algebra. I think you guys are all probably familiar with this. Nothing crazy. And then previously, before, we were actually looking at basically a spanning set of one vector. So we could have like rewrote that question, but that's fine. So yeah. And then this is a very standard linear algebra lemma. Let S be an ordered set of vectors in V, and W is a subspace of V. If S is a subset of W, then the spanning set of S is also a subset of W. Which, in a way, like kind of makes sense. Like if every vector S is in W, then we can combine any vector and it will still be in W because W is a subspace. Which is basically the proof for it. You can take any vector in the span of S. This is obviously an element of W. So yeah, because we can write it in terms of this, then this element will also be in W, which is exactly what we want to show. The span S is a subset of W. So yeah. Well, let me check the recording. Yeah, we're good. Okay. Wow, we're actually moving kind of fast. Maybe I should slow down. So an ordered set of vectors S is said to be independent or linearly independent if there's no linear relation. So basically if there's no vectors, sorry, not vectors, scalars that make this zero, except for when all of them are zero at the same time. And so linearly dependent would be the opposite of this, that there exists a non-trivial case that makes the linear combination zero. And then we come across this is also another standard lemma. A set V1 is of one vector is independent if and only if that vector is non-zero. And then there's a statement about two vectors being independent. They're not scalar multiples, because if they were, then we could rewrite them. Rewrite one as the other one, and then it's kind of redundant to have it. And then any reordering of an independent set remains independent. So we could write it any way that we want. We could write V2, V1. It doesn't matter. Okay, I think these sections are longer, so that's why we're like so quickly through all of this. So a basis, also straight from linear algebra. This whole chapter is just linear algebra. There's nothing crazy going on. A basis is a set of vectors that is both independent and it generates the entire space, or that it spans the entire space. So it has to have the first condition we talked about, being independent. So only the trivial case can make this 0. And we can rewrite any vector in the larger space as a linear combination of these vectors here. And then in the chapter, I think they denote basis by this bold B. You'll also find it's denoted by just B, or maybe beta. Yeah, we can also rewrite this second condition as just V equals span of beta. Or B, sorry. So here's an example of a basis. The set B with standard coordinate vectors, E1, E2, and E3. I wrote down what these are because I think he covers them like a little bit later, but that's fine. I think most likely if you're reading abstract algebra, you've been through linear algebra, I would hope. So that's all good. And this set is a basis for R3 because it is independent. We can't write E1 as E2 or E2 as E3 and E1 or something like that. And it spans every single vector, which means that we can basically write any vector in R cubed as a sum of scalar multiples of these. Kind of like building blocks for the vector space. Wait, hold on. Okay, hold on. Let me actually pull up this, because this theorem actually did not get copied into the presentation properly. What is that theorem? That is 3.4.14. So 86. Let me just grab the actual proof of that theorem, or the theorem itself, because I have the proof here, but I don't have the theorem. That is 3.14. Oh, okay, here. Can you guys see this? Yeah, you see the book? Okay, this is Artin. Yeah, this is the proposition that if there's a set B, which is a basis for V, if and only if every vector W in V can be written in a unique way. So, yeah, he uses what's it called? A lot of like vector multiplication and matrix multiplication throughout this chapter, mostly to like keep explanations and proofs very concise. So yeah. And then the proof for this, we assume that B is a basis of V, then it's independent and spans V, the two components that make it a basis. Then we suppose by contradiction that there is some W in V that can be expressed in two different ways, so it's not unique. So we can rewrite W as B times X and B times Y. This is just vector multiplication with a list of constants C1 to Cn, D1 to Dn, such that these two are not equal. So this is just like a condensed way of writing out two linear combinations being equivalent. NB in addition 1, this is proposition. What is NB? Oh shoot, okay. 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 And then we can subtract these two representations on both sides to get 0 equals the basis times x minus y. And since b is independent, the only solution to this would be that x minus y is 0, which implies that x equals y. But this contradicts, obviously, that these two are not the same. So therefore, we can write any vector uniquely in a basis using basis vectors. And then for the reverse direction, if we suppose we can write any vector uniquely, we want to show that B is independent. So if we suppose that, that this is equivalent for some scalars. If B were not independent, that means that there was a trivial way to get 0. This would mean that 0 could be technically represented in two different ways. Both as a trivial and non-trivial combination. But this is impossible because 0 can only be represented in one way. And then part 2, yeah. We also have to show that B spans V as well. So that's independent and it spans it. So assume there's some vector, W, that can't be expressed as a linear combination. So we're doing contradiction again. And this would mean that there's a vector in B that can't, a vector in V that can't be represented in B. So it doesn't span V. But we assume that every vector in V can be uniquely expressed using B. So, yeah, this proof is kind of a little bit redundant. Like, it's a little bit obvious that, oh, if I can represent any vector uniquely, then it has to span V. Because every single vector can be written as it. So I definitely would shorten this a lot. I think it's a little too convoluted. But yeah, that's just the idea. That's the basic idea behind it. So now we actually talk about the standard basis and the vectors. We denote it as bold E, and we denote V as f of n, where each of the vectors can be represented like this, where EI is the ith place of wherever that 1 is. So if we had E2, it would be up here. You know, further down number, it would be down there. And I think we talked about Fn in the last lecture, like very briefly, in the last video lecture. This basis here spans all of Fn. This is like in part a definition, but also like, I guess you could say an example as well. I think other books probably write this as an example. It's also linearly independent, as we saw before. With R3, we had like E1, E2, E3. So it's the same concept. So if we let S be a ordered set of vectors, and W be any vector in V, we can append a new vector to S written in this way, which I actually really like. I like that he wrote it out like this instead of like the union of unordered set, which is usually how other books would write it. Then we have that span of S is equal to the span of this new set, adding W, if and only if W is already in the span of S. So basically, there is no new information that's being added to the spanning set. And then if S is independent, then S prime would be independent if and only if it's not in the spanning set. Because if it is in the spanning set, then we could rewrite it in terms of other vectors that are already in the set, and so it wouldn't be independent anymore. Yeah, I think I gave some intuition behind this. Yeah, that's basically what I explained. It gets absorbed into the spanning set in part A. And then in part B, yeah, it can't be written as a combination that already exists in S. So I think this part is also quite long too, but I'll have to see. So we're gonna talk about dimensions of vector spaces. That's like the last part. So a vector space V is called finite dimensional if some finite set of vectors spans V. Otherwise, we just say that it's infinite dimensional. And for the rest of this lecture, we will assume that every vector space we are working with is finite dimensional. So we won't worry about infinite dimensional vector spaces. But it is a very interesting topic. It's also an annoying case that you have to consider when you're working with dimension. Like, oh, what if it's infinite? Then does this still hold? And so some things actually, they get a little wacky in infinite dimensions. Yeah, no, it's definitely like a annoying case to consider. So just to not deal with that, will only be finite. So let V be a finite dimensional vector space, and S be a finite subset that spans V. And let L be an independent subset of V. Then you can obtain a basis of V by adding elements of S to L. So basically L is this independent set, and it will be smaller than whatever the basis is. And so if we keep on adding elements and retain the independence of the set, we will eventually reach a point where we're in like this middle ground, like we're both spanning the entire space and we're also independent at the exact same time. And there's actually like sort of a squeeze theorem in a way that I'll show in a couple slides to give a better representation of this. Let S be a finite subset that also spans V. Then we can delete elements. So yeah, spanning would be like anything larger. We'd basically overshoot that we have like independent, it's dependent, that we have like these extra vectors that we don't need, that are just kind of unnecessary. So if we keep removing them, we'll eventually like reach a basis. And the previous proposition actually showed us how to add elements of S to L, right? Because what's it called? If we add an element to the spanning set of this, it gets absorbed, right? So there are two cases. Like if we add something, it'll get absorbed, and if it's already independent, right, and it's not in the span, then we can we can add it and like keep adding. So hold on. So yeah, here's a better way of writing out this inequality that we're looking at. That if S and L are finite subsets, and that S spans V and L is independent, then the size of S is going to be greater than or equal to the size of L. There's like this. There's basically just this balance between the spanning set and the independent set, and the basis lies like in the middle of this inequality here, which I think I write. Yeah, right here. There's like a kind of a squeeze theorem for it. This is the independent set, this is the basis, and this is the spanning set. So the proof of this, at least the proof that he wrote in his book, is not too complicated. If we let S and L be ordered sets of size m and n, and assume by contradiction that m is less than n, so this is false, and we know that the spanning set of S is equivalent to V, we can assemble the elements of L in terms of a system of equations from S, which we call A. He goes into more detail about how he assembles A. It's like a list of equations using the columns of this this matrix right here. You can take a look in the chapter. It'll give a more detailed breakdown. But this is the main idea. And then he writes SA, which is equal to L. And so yeah, this makes sense because we rewrote the elements of L in terms of equations from S. So this is basically what we're forming right here. Then we can write this as Lx is equal to SAX. So X is just a matrix of, a vector, matrix of unknowns. And if AX is equal to 0, then Lx will also be equal to 0. And we know that AX equals 0 has a non-trivial solution, and therefore L is dependent, which contradicts that L was independent. So we must have that M is greater than or equal to N. Yeah, there's more steps involved in that last part, which I cover in this slide as well. The equation AX equals 0 is homogeneous, so it always has the trivial solution, x equals 0. But since m is less than n, we have basically more unknowns than equations. We'll have a non-trivial solution. And then the other part of the question, we used associativity to rewrite this as SAX instead of SAX. So yeah, that's basically the idea of this proof. This is not like a formal proof, but this is basically what he does. And then let's see. So yeah, this is the squeeze theorem I wrote. I thought this is like kind of funny because I know calculus has a squeeze theorem, so I thought that'd be this is usually how I think of it in terms of like an inequality. So we add more vectors to this, we get a basis. We take away more vectors from the spanning set, we get a basis. So let V be a finite dimensional vector space. Any two bases of V have the same number of elements. Yeah, this actually makes a lot of sense if you think about the last theorem we did. You could basically apply the basis to both of these elements. Well, if we had one basis and another basis, then obviously it spans, and and the other one's independent, because those are the two components, then the size of B1 would be greater than the size of B2. And we could just basically flip them. B2 is also spans V, and B1 is also independent, so by both inequalities they would have the same number of elements. Yes, and then the other two parts are kind of similar. Let B be a basis. If we have a finite set S of vectors that spans V, then the spanning set S is greater than the basis, which is like what I talked about here with the squeeze theorem. And these two sets would have the same number only if S is a basis. Basically, we removed some, and now we're at a basis. And the same thing could be said here. If we have an independent set, then it's less than B. If we add more vectors, we'll get exactly the basis. So yeah, this is basically what this is saying right here. Yeah, I think I already explained the proof of this. Yeah, take by theorem 3.4.18. That's the previous one we mentioned. We could just take both bases and get two inequalities. Here's one, here's the other, and by both of them we'll get that they have the same number of elements. I think for the other parts of this, you could probably spam the same theorem, and probably some of part A, but I thought I would leave that out because it's kind of similar. It's a similar process to this. And then now we arrive at the actual definition of dimension. We've been talking about the size of the basis, the size of independent sets. And so there's a word to describe the size of the basis, which is the dimension of the space itself. So we write it as dim of V to represent the size of the bold B. For finite dimensional vector spaces. I don't think this makes a difference though, if it's finite or infinite. But anyways. So previously we talked about Fn, which is like the column vectors. And the dimension of this space would be n, because we have exactly n vectors in that space, which we can write like this. So this is standard. It's just a number. That's all that the dimension is. And if W is a subspace of a finite dimensional vector space V, then W is also finite dimensional. And the dimension of W, so the size of its basis, will be smaller than the size of V. The size of V's basis, which kind of makes sense. I mean, W would be like literally smaller, so obviously we need less elements to span it. And these two would only have the same dimension if they were equal. That means they're the exact same space. Which I guess is kind of intuitive. Like, you know, if they both have the same number of spanning vectors, and both same number of basis vectors. Yeah, maybe not as intuitive as I thought, but it's an interesting result nonetheless. It's a very useful one too. So we'll prove this proposition here. Yeah, we prove, let me see, yeah, the whole thing actually. So if we start with some independent set L that could be empty, it doesn't matter if it has an element or not. And if the spanning set of that set L does not equal W, right? We're not spanning the whole space. Then we can choose any vector that's in W that can't be made using the spanning set, and we'll add it to the spanning set. Basically, our spanning set is too small. And eventually, we'll continue this process of just adding vectors, and we'll get an independent subset of W. So by our previous theorem, the size of L will be less than the dimension of V, which is what we talked about back here. Basically, the squeeze theorem. It's an independent set, so it would be less than the basis. And then from here, we can basically continue adding elements until we have a basis. And then eventually we will have a basis for W, which is less than the dimension of V. I think I wrote, think about the squeeze theorem for this question. And then if we're able to, but let's say we didn't stop, right? And we kept going, right? Like the size of L kept growing beyond the dimension of W, right? Like we kept adding. Then we would actually arrive at that the absolute value of L is exactly the dimension of V. So then that same L, which would be a basis for W and V, would mean that V is equivalent to W. Let me see. Yeah, I think that's it actually. That's all I had. That was like half the book. But I could technically cover the rest of the chapter, but yeah, wow. Actually, I think I flew through those slides really quickly. So, if we want to go back and like look at certain slides, we can. Yeah, I was looking for this to be like an hour long maybe, but I guess we didn't quite reach there. So sorry, say that again. Oh, usually I think it's standard in abstract algebra that they cover a small section of it. I think it's used to help connect back some of the ideas that you learn in group theory. Yeah, I think it's usually just a standard practice to do it. But in terms of why, I think it's just because linear algebra is like a subsection of abstract algebra in general, they usually just end up covering it at least a little bit. I think Artin, the book that we're using, spends more time with it than I've seen other books spend. They usually cover like only a couple sections and then move on. Yeah, maybe. That could be why. I don't know how many abstract algebra books get up to modules. I think I have one book that goes all the way up to modules. Galleon doesn't. Um, so but yeah, that's what I would. That's what I would say for covering vector spaces. He does cover quite a bit though. Like, oh, okay. Let me take a look.
Yo, we gotta go out soon. Start grabbing some food.
Yeah, I know. Give me a second in the presentation. Yeah. 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 Usually fields are taught after rings. I think fields have more properties than rings do. Or is it less? I can't. Yeah, yeah. Actually, I think part of this chapter he goes over fields in vector spaces. I didn't cover it because it was very small, and I feel like fields, finite fields, is like a pretty big topic. But there's not much to miss. It's similar to typical linear algebra covering. Well, they'll just talk about like, oh, you can cancel out elements in a field, but they don't explain very much. Yeah, I agree. Let me see. What else can we do here then? We could. I'm actually not too sure. I don't think I've ever covered modules, so. Mm-hmm. Yeah, they cover a lot of linear algebra in Artin. They go over all the way up to Jordan form too, which is surprising. I think they go through it very quickly though. So I'm curious, uh, how much content is usually covered in a lecture? Since I've seen them be like an hour and a half long. Okay. Okay. So, okay. Gross's lectures.